Sorry, I just read the sketch of proof, but I think you got it. So I will now prove the theorem, and the first lemma is the one about compactness and improvement of flatness. So there exists a constant epsilon 0 in 0 infinity, a scale theta in 0, 1 over 2, such that for all b in Rd, in R3, for all UP local suitable weak solution to the Navier-Stokes equation with drift, if two things, so the first thing is the integral over q1 of u cube 1 over 3 plus the integral of q1 of p3 over 2, 2 over 3 is smaller than epsilon naught, and b is smaller than 1, then the oscillation up theta is bounded by theta to alpha times epsilon 0. Okay. So the definition of the oscillation is here, and again I stress that the mean in P here is only under space ball B0R, and the mean here is on the whole QR. So for the proof, like this morning, the first step is to consider the limit equation and to have the bound for the limit equation. Consider limit equation. And fix, so the goal is to fix theta and alpha. So since we have the smallest assumption, the limit equation will be just linear. So it will be linear Stokes. So dtu plus b dot gradient u plus so minus Laplacian u plus gradient p is equal to 0 and divergence u is equal to 0. And this is in so again, like this morning, the limit equation will be considered in the smaller ball. So here q 2 over 3. And I have b smaller than 1, and I have v in L3 of q3 over 2, which is, sorry, I denote this by u, maybe I should use v. Sorry for this. So v in S3 L2 over, so q2 over 3 in the smaller hyperbolic ball is bounded by the measure of q1 1 over 3. So this, forget about this. This is just technical, just to get the right constant in there. And again, I should call the pressure q instead of p. So q in L3 over 2 of Q2 over 3 is smaller than Q1 1 over 3. Okay. So I have bounds on these solutions, and I know by regularity theory for the linear Stokes equation that the solution to this equation is regular in space. So I will not at all talk about how to get such regularity estimates for the linear Stokes, because this is not the point I want to talk about, but I just state that by regularity theory for Stokes, which is linear, you get that V is C13. So C13 core, so space-time parabolic cylinder of Q23. And because of that, by Campanato, you can estimate the mean over Q theta of V minus V theta which is smaller than a constant times T2 or 3 times Q1 2 or 3. Just yeah, sorry. I think I forgot something when I stated the characterization of the Campanato or Campanato characterization of Hölder continuous function, which was so in the Campanato characterization. I have, I forgot the scaling factor. So I have the sup over x naught, t naught, and r of 1 over r alpha times p qr x naught, t naught, the mean. And then the rest was correct, smaller than infinity. I completely forgot this factor. So sorry for that. And now I'm noticing because we're... And so actually I think there's a slight mistake in my lecture notes. So here, I'm wondering whether this is 1/3 or 2/3 now. I think this is 1/3. No, sorry. No, it's 2/3. Okay. Okay, so there, so we can estimate this time, this space mean like this. So for their velocity, and so the reason I'm slightly confused is because of the parabolic parabolic Holder continuity, which is alpha, exponent alpha for time, and 2 alpha for space. So I must say, I don't really remember now if it's the alpha for time or alpha for space here, but I will stick to my notes. I think it's correct in my notes. So I think here it's 2 for. So, okay, so this gives me the estimate for the velocity. And their estimate for the pressure is given by the fact that I have Laplacian Q, so it's linear equation, and the divergence of this term is 0. So there, I get Laplacian Q is equal to 0 in Q 2/3. So by the regularity for the linear equation, I have that, so in space, so regularity in space, for harmonic equation, so I get the integral over B0 theta Q minus Q theta T. So I'm applying this for fixed T. I'm considering this equation, and I'm using Lipschitz regularity theory. So this is smaller than C theta B0 2/3 Q 3/2 2/3. And now I can integrate, so this is for fixed T, and I can integrate this in time. So if I integrate in space and time, I get theta times the mean over Q theta of Q minus Q theta at time t, 3/2, times 2/3 is smaller than C theta 2/3 Q theta Q 2/3 of Q 3/2, 2/3, and all this is then smaller than a constant C1 times theta 2/3. So I call this here C0 times theta 2/3. So I call this constant C0, and I call this one C1. So I will do that later also, estimate separately velocity and pressure. And now I will choose theta, so I fix alpha smaller than 1/3. And I will choose C0 theta 2/3 plus C1 theta alpha/3 smaller than 1/2 theta 2 alpha. Yeah, I think now there. maybe I'm too tired to see it, but I think probably the exponent here is 1/3 instead of 2/3. But let's be consistent and write 2/3. Maybe there's something to check after the lecture, but I would just try to be consistent. But there, yeah.
Maybe 1/3.
Yeah, I think 1/3, but if I change it now...
Scaling.
Yeah, right. But if I change it now, it will propagate. But thank you. And here I think I made the mistake because of the first lecture where I wrote means over B0 rho or B0 theta, and something had to be smaller than theta 2 alpha, and I didn't take the 1/2 here. But now I'm considering the quantities, the actual norm, so alpha would appear here. So I think the confusion comes from the first lecture. But as I told you, let's stick to the notation I adopted in my lecture, otherwise it will be very confusing. All right, so, but in essence, the argument, this does not change the proof and the argument. So the key thing is we choose alpha smaller than 1/3, and we take theta sufficiently small such that this holds. And again, as this morning, we'll do a contradiction argument. So there, step 2 is a beginning of contradiction argument. Okay, so I will assume that I have a sequence epsilon k, which goes to 0, which corresponds to the smallest parameter, and the sequence of functions uk, pk, which are local suitable weak solutions to the Navier-Stokes wave drift, and I also have a bk, which is smaller than 1. And I assume that UK 3, so the mean over Q1 plus the mean over Q1 of pk 3 over 2, 2 over 3, is equal to epsilon k. So this is one thing, and the second thing is that my inequality in the end is false. So I also assume that the integral over q theta uk minus uk theta 3 1 over 3 plus theta q pk minus pk theta t 3 over 2 2 over 3, that thing is bigger than theta 2 alpha epsilon k. Okay? So the whole proof is this gives me a bound on the solution. So I get some compactness thanks to local energy inequality. And this compactness allows me to pass through the limit here and to get a contradiction. But in order to do this, I will first rescale my functions. So I will first rescale the functions and consider Vk, which is uk over epsilon k, and pk, qk, which is pk over epsilon k. And in that case, I have these here I can just replace UK by VK, PK by QK. I have one here, V, QK, and I get that this is 1. Okay? So now it's much easier to use the compactness properties. So VK, PK, QK is a local suitable weak solution. True. So instead, so this is kind of different this morning. Here we just divide the solution by epsilon k. We're not rescaling the solution. So it's a weak solution to Navier-Stokes with drift. But with some small nonlinearity. Okay, so here we have again the smallness parameter, and when we let epsilon k tend to 0, this will disappear and will just converge to the linear Stokes equation. So by just using weak convergence, we already know from the bounds on the solutions. So, from the bounds, we get that V converges weakly in S3, and QK converges weakly in S3 over 2. And we get that their limit in S3 of Q 2/3 or Q1 is smaller than the lim inf of the VKs. And this is bounded, and in the same way for Q in L3 over 2 is also bounded by 1. So we have these two bounds, first bounds. But this is not enough. We need to get some strong compactness in order to pass to the limit. So the step 3 is actually getting strong compactness. So in order to get strong compactness, so this is quite classical in this theory, and we use this argument quite often, but it's not so trivial. So the goal is to get that Vk converges strongly to V in L3. So this is the claim. Okay. And so from the local energy inequality, which is satisfied by Vk and Qk, you know that, so I don't write the whole inequality again, but we have that the integral over R3 of Vk dot t square phi dot t plus 2 times the integral between -1 and t over R3 of gradient V square is bounded by some space-time integrals, but the space-time integrals only involve the u cube and p times u. So all this will be bounded uniformly in K because Vk is bounded in S3 and Q is bounded in S3 over 2. So we have a uniform bound times phi. So we have a uniform bound on this local energy, thanks to our assumption. And this local energy, you see that I control the solution in. So from this you get that Vk is bounded uniformly in L infinity in time, L2 in space, intersected with L2 in time, H1 in space of Q 2 over 3. And Qk, and yeah, so this is the first result. So Vk uniformly bounded in that space. But this is still not enough to get strong compactness, because here we control the H1 norm in space. But in order to get strong compactness, we also need to control some strong norm in time, so some time derivative of the solution. So this first result implies that Vk is uniformly bounded in L 10 over 3 in space and time. So this is simply a Hölder inequality, basically. Hölder inequality plus embedding of H1 in S6. Okay, so now I would like to outline how to get the estimate for dTu. So I need to get an estimate for dTu. And for this, I use the equation. So I test against phi. So phi is C infinity compactly supported in Q2 over 3. So this is smaller than so here I use the equation. And I bound the space-time integrals I get as follows. So Vk, greater than Vk in L3 over 2 in time, L2 in space, Q2 over 3. Nabla phi in L3 in time, L2 in space in Q2 over 3. Plus B plus epsilon k Vk in L infinity in time, L2 in space. Nabla Vk in L3 over 2 in time, L2 in space. Phi in L3 in time, L infinity in space. And I have one last term which is related to the pressure, Qk in L3 over 2 time and space, and phi in L3 in time and space. So in the end, everything is bounded by a constant, because all these quantities are bounded uniformly in K, times phi in L3 in time, H2 in space. So from this I get a bound on dTu in L3 over 2 in time and some weak subleft space in space. So I get a uniform bound on dTu, or this is dTv, sorry. So dTvk is uniformly bounded in L3 over 2 in time, and H, the dual of H20 in space. So the important thing is I have a bound on space derivative of Vk in some LP space, L2 space, and I have a bound on a time derivative of the solution in some LP space in time and some weak space in space. And from this, I can apply a classical lemma in the theory, which is called Aubin-Lyons lemma, which gives you some compactness. So by Aubin-Lyons, Relish lemma, you have compactness of Vk pre-compact in L3 in space and time. And so from this plus interpolation, so plus Hölder, you eventually get that Vk converges strongly to V in LQ of Q203 for any Q in 1 10/3 excluding. Okay, in particular in L3. So from the strong convergence in L3, you can pass to the limit here. So now the next step is passing to the limit and getting the contradiction. So if you pass to the limit, so you can take the lim sup in this equation and get that theta 2 alpha is smaller than, so the lim sup, so the first term is converging. So you have the mean over q theta of v minus v theta 3, 1/3. And then plus theta times the lim sup when k tends to infinity of the mean of qk, qk minus qk theta of its time 2/3, 2/2, 2/3. Okay. So you still have to analyze this term. So this term will control using the velocity. So we need to control the pressure. So the difficulty of controlling the pressure is that we have no formula linking the pressure to the velocity because we don't know anything about the solution outside our domain. So we decompose the pressure, so Qk, but the feature that helps us and that eventually makes it possible to control the pressure is the a priori bound we have on it. So we decompose the pressure into Hk plus Gk, where Hk is So HK is the solution to the harmonic. Is a harmonic function in Q2 or 3, and GK it's in space only. So I fix time, and I consider this in B2 or 3. And I'm also imposing that the mean over B0 to 3, B0 theta of HK dx is equal to the mean of QK. So I can, HK is defined up to a constant, so I can always define it like this. And minus Laplace, so GK is solving a boundary value problem. In B0, 2, or 3. And I'm imposing zero boundary condition on the exterior and on the boundary of the ball. All right. So the first thing is I can estimate GK. So GK now is uniquely defined, and I have a representation formula, and I can use Calderon-Zygmunt type estimates. So by Calderon-Zygmunt, I have that nabla GK in L9 over 8 in space, B0, 2 or 3, is bounded by VK. So it's actually there is an epsilon k here, because there is epsilon k in the equation. So their nonlinearity is weak. Don't forget this epsilon k in the equation for the pressure. So epsilon k, Vk dot gradient Vk in L9 over 8. Okay, and so I can bound. So now, if I integrate in time, plus use Poincaré-Sobolev inequality, I get that the integral over Gk 3 over 2, 2 over 3, over Q 2 over 3 is bounded by, of course, the quantity, so the slightly higher Bldg exponent, Gk, so 9 over 5, 5 over 9. And now I use Poincaré-Sobolev inequality, so to bound this by the gradient. So let me write the gradient of Gk in L3 over 2 in time and L9 over 8 in space. And this now is bounded by our C epsilon k of Vk dot gradient Vk in L 3 over 2 in space, in time L9 over 8 in space. And since Vk is its local energy is bounded, this quantity is finite. And so from the bound we had before, from this bound here, you can bound this by c times epsilon k. Okay? So this gk actually goes to 0. And thanks to gk, we can now estimate hk. So we have okay. So we have so hk. You use just regularity for harmonic functions. So for hk, by the Lipschitz estimate we wrote before, of step 1, if you remember, we have theta times the mean over q theta, hk minus hk theta, t 3 over 2, 2 over 3 is smaller than c t theta 2 over 3, q 2 over 3, qk 3 over 2, 2 over 3. Plus two over 3 of gk. Okay. So this is because I can bound by their mean of hk over q2 over 3, but hk again I can use the bound. So I have an upper bound on qk and gk, because hk is equal to qk minus gk. But this is what I did on the right hand side. So in the end, I get that all this is bounded by c1, which is the constant we had in step 1, if you remember, times theta 2 over 3 plus c times epsilon k. Okay? So now I have bounded, so the term which I so when I pass to the limit, yeah, here. So here this is a limit term, so this is good, and now I can bound this term. I can bound this term by C1 plus something which goes to 0. Okay? So here, if I go back here, I can bound all this by C1 theta 2 over 3. And since it's the lim sup, it's the epsilon k goes away. And okay. So now we have the contradiction. There's just one additional comment I want to make. So this here is the constant C0 we had before. For some reason, I cannot remember now, but so you get, in the end, you get C0. Okay, so sorry, no. This term here, by their Stokes by step 1 is bounded by C0 2 over 3 by step 1. So all this is bounded by C0 plus C1 theta 2 over 3. Okay? And now you get a contradiction because we assume that this is smaller than 1/2 theta 2 alpha. So 1/2 of theta 2 alpha bigger than theta 2 alpha leads to a contradiction. Okay? So this proves the lemma. So it's a little bit more involved, but just because of the pressure. But the general idea is along the same lines as what we did this morning. So so for the end of the lecture, let me state lemma 2 and some historical comments about their suitable solutions. And let me finish by the partial regularity theorem for the Navier-Stokes equation. So I guess it will take me like 20 minutes or something. So, so lemma 2 is the iteration. So now iteration becomes very easy once you have set up everything. So you assume that, so you let theta, alpha, and epsilon not be given by lemma 1. And for all k in N, and for all local suitable weak solutions to Navier-Stokes equation in Q1, if the mean or so if the oscillation of u p theta k is smaller than theta 2 alpha k epsilon 0, then, and the condition, so this is 1, this is 2. So this is what replaces the smallness condition we had in the first lemma. And 2 is a condition on the B. So theta k u theta k is smaller than 1. So this will be the B, the drift. So if this is true, then you have the estimate at scale theta k plus 1. So then oscillation of u p theta k plus 1 is bounded by theta 2 alpha k plus 1 epsilon 0. Okay? So, so the proof goes as follows. So we consider rescale functions. So the idea is to go back to applying lemma 1, as we did this morning. So we just have to consider the right rescale functions. So u of x is the function u of theta k, so x and t, theta k x, theta 2kt, minus the mean over theta k over theta 2 alpha k, and p is P of theta kx, theta 2k t minus P theta k of theta 2k. So this mean again is depending on time, and I divide this by theta 2 alpha minus 1 k. So now you see that these functions are very nice because so first you have that the mean of u over q1 is 0, and so is the mean of over b01 of p evaluated at theta 2kt. And by assumption by assumption 1, you have that the mean of u cube over q1, 1 over 3, plus the mean of p 3 over 2 over q1, 2 over 3, is bounded by 1, by epsilon 0. So you have the smallness condition epsilon 0, which is satisfied by these functions. And furthermore, u and p are local suitable weak solutions to Navier-Stokes with drift. And the drift is plus or minus theta k u theta k. Okay. So because you have all these properties, you can apply lemma 1 and get that the oscillation and get eventually the result. Okay. So there is one thing I need to check is that the mean over theta k plus 1 is smaller than 1. Here. So there is one thing which is to check that theta k plus 1 u theta k plus 1. So I agree, I'm hiding some computations, but it's really just computations. The idea is there. So this you can bound by theta k plus 1 u theta k plus 1 minus u theta k plus theta k plus 1 u theta k. So if you take theta smaller than 1/2, you can bound this by 1/2 of theta k. So all this term will be smaller than 1/2 by assumption on u theta k. And the first term you can estimate using the oscillation. So that term here you can estimate as theta k plus 1 theta minus 5 q theta k of u minus u theta k 3 1 over 3. And so this, you know, is small. So eventually choosing epsilon naught. So all this will be smaller than theta k plus 1, theta minus 5, theta 2 alpha k times epsilon 0. So choosing epsilon naught sufficiently small in the previous lemma, so smaller than theta 5 over 1/2. So if you choose epsilon naught smaller than theta 5 over 2, then you get that all these inequalities finally, all these quantities are eventually smaller than 1. Okay. So here you need to make a right choice of epsilon in the previous lemma. So you can always make epsilon smaller. Okay? Because theta is fixed independently of epsilon. So this ends the proof of the iteration lemma. So everything, the whole work is done in the first step, basically. Okay, so let me do some comments about regularity. So we proved regularity in C alpha norm. So we proved U in C alpha parabolic. But actually, you can get that our solutions are much more regular in space. Not in time because of the serine example, but in space you can get much more regularity. And this is due to work of serine, Strover. Okay, so there are many people working on this. Ladizanskaya, Prodi, Takahashi. So there are many different proofs, and which states that if you have a solution U in L infinity L2, so L infinity in time L2 in space, intersected with L2 in time L2 in space of Q1, and so U, if additionally U belongs to LP, LQ in time and space of Q1, then U belongs to C infinity in space of Q1. So U is smooth in the space variables. And so this works for P and Q, such that 2 over P plus 3 over Q are smaller than 1, and works for all P between 2 and infinity, and Q in 3 infinity. So actually this smoothness, you don't know a priori that it holds for the solution we're considering, because if you take any solution like this, you will only get that it belongs to LP or LPLQ for 2 over P plus 3 over Q equal to 3 over 2. Okay, which is bigger than 1. So you don't get the, this condition is not necessarily satisfied here for the solution in this class, for which the local energy is bounded. Okay? And there is a gap which is which explains why it's not so clear how to get the regularity, smoothness of solution to Navier-Stokes in 3 dimensions, just knowing that the energy is bounded. So for the moment, it's not possible to bridge this gap. But by our smallness condition criteria, by assuming that this L3 norm of U plus L3 over 2 norm of the pressure is small, we get that U is in the parabolic is Hölder continuous in space and time, and so this condition is satisfied. So we know as soon as you have some alpha of the solution is Hölder continuous with some exponent alpha in space, you know that it's C infinity in space. So there is a more quantitative result which you can find in a paper by Nekas Rosica and Sverak, which tells you that if 1 over r squared QR U3 plus P3 over 2 is smaller than epsilon star, then nabla K U is in the parabolic cylinder, so space-time parabolic cylinder in Q1 half, QR over 2 bar, and you have that the supremum of nabla K U of QR over 2 is smaller than R minus 1. So CK R minus 1 minus K. Okay. And I would like to mention one more thing about the endpoint result in this Severin criteria, which is the point P equal to infinity and L3, and that is due to Escorias-Serkin's work. Okay. So if some of you need to leave now, of course you can just take 5 to 10 minutes more to tell you a bit about the history of the results and about the partial regularity. So
excuse me.
yeah.
The proof given in this lecture,
Yeah.
The estimation of alpha is any alpha less than
1 over 3.
1
yeah.
over 3.
Yeah, yeah.
Okay.
Strictly less. Yeah.
That's good.
Mm-hmm, mm-hmm.
Okay, thank you.
Yeah, yeah. And this is because we are assuming integrability for the pressure in L3 over 2 that we get there. And strictly less is because of the compactness argument. Okay, so just a word about the history of the result. So I will write 2 columns. So one about the Le-Rayhoff solutions. So Le-Rayhoff solutions are their finite energy weak solution to the Navier-Stokes initial value problem. So I told you about their global energy for the Navier-Stokes equations. So these solutions are when you start from initial data in L2, divergence free, you have a global control of the energy. So this is a theory of the initial value problem. And here I want to talk about local suitable weak solutions and epsilon-regularity. So their story starts in 1934 with work of fundamental work of Loret, proving the existence of these weak solutions with the global energy being bounded, and extended by Hopf in 1951 to the case. So Loret was for the whole space, and Hopf was for bounded domains. And but these works do not give you information about the pressure. So they're having estimate on the pressure is non-trivial. So in the case of R3, thanks to Calderon-Zingman theory, you have that, so remember the pressure is solution of their minus Laplacian is equal to divergence U gradient U. So, and let me even write it like this. So if so we know that if the local energy is bounded, or the global energy is bounded, we have U in L10/3 space-time. So U squared is in L5/3 space-time, and so P is expected to be L5/3. So in the case of R3, you can prove this. But until the work of Sohr and von Waal in 1980-something, 6, this result was not known for the case of bounded domains or domains with boundaries. But they prove it also in the case of boundaries. And in the case of boundaries, it's non-trivial because in addition to having this equation for the pressure, you have boundary condition for the pressure. And the boundary condition for the pressure, in order to estimate them, you need some smoothness of the initial data. So this was for smooth initial data. And so parallel to this layer of solutions, you have the theory about local. So this is initial value problem, and this is local problem. So the local suitable weak solution. So there's fundamental work about this by Schaeffer in 76, 77. And he introduced the notion of suitable weak solutions. So solution for which you could localize, and also proved the first partial regularity results for Navier-Stokes equations. So this is pioneering work. And then you have work by Caffarelli, Cohn-Nirenberg, which managed to have the local version of the theorem. So this was in 84 or 82. But they did not. They could not rely on the result of Sohr and von Waal about the pressure. So they didn't know that they guessed that the pressure would be L5/3, but they could only work with P in L5/4. So in the definition of the suitable solution, we had L3/2. They could only have 5/4. And then, so these two proofs are iterative. And then Lin in 1998 gave a compactness proof, so the proof I showed you, with P in L3 over 2. So of course the P would be more regular L5 over 3, but L3 over 2 makes everything work nicely. And Ladizanskaya and Seregin also proved kind of rewrote the compactness proof, extending it a little bit, of Lin, in 1999. And they noticed that their L'Oreal solutions, the pressure for the L'Oreal solution belongs to L3 over 2 for any initial data, but only starting from some positive time. And also, of course, in space. And you have different proofs by Vasseur in 2007, which use a de Giorgi type approach to prove the compactness terms. And so Vasseur and Kukavica in 2009, which has an argument, who has an argument which is closer to the one of Kafarleko and probably other people also. So this might not be exhaustive. Okay, so now I would just like to finish by saying something about partial regularity. So the key idea is that you have a nonlinear equation. You control, for example, the energy, but the regularity we proved depends on the smallness criteria of some quantity. So the this quantity will not be small everywhere, and so you will only get almost everywhere. So you will only be able to get the smallness of this quantity almost everywhere, so the smoothness almost everywhere. So, So I will not give proofs here. I will just state the result, and if you have questions, you can of course ask me. So there is another epsilon-regularity criteria, which I call the lim-sup criteria, as opposed to the U plus P, and which was already present in the work of Kafarleko and Bldg, which states that there exists epsilon 1 in 0 infinity, such that for all UP local suitable weak solution to Navier-Stokes in Q1, the lim-sup when R tends to 0 of 1 over R QR gradient U square is smaller than epsilon 1 implies that there exists rho strictly positive such that 1 over rho square Q rho U cube plus P 3 over 2 is smaller than epsilon star. So the epsilon star is the one of the lim-sup lemma. So that basically tells you that if this lim-sup is smaller than epsilon 1, then the condition, the smallness condition of the U plus P epsilon criteria, which we proved before, is satisfied. And if this is satisfied, then your Hölder continues in space and time. And why do I state this result? Because this result has the important implication which follows. Which is that their parabolic host of measure H1 of the singular set, so we'll define the singular set, is equal to 0, which means that the dimension, so the host of dimension of the singular set is smaller or equal to 1. So let me just make some comments about this. So the singular set typically is their set of points of their space-time at which the solution is not smooth. So I say that a point xt is regular if there is a point, so xt in Q1 is regular, if there is a point, if U belongs to L infinity of QR xt for some R. Okay? And xt is not regular, is singular. If U does not belong to L infinity QR xt for any R, because it's, so U is singular basically if U is not, xt is singular basically if xt is not regular. And I define S as the set of points xt is singular. So we don't know actually for Navier-Stokes equations if there are blow-up points, if there are singular points, but what this result tells us is that if there are singular points, there are not too many of them. And in the sense that their host of measure, so parabolic host of measure is just defined with, instead of taking balls, you take parabolic cylinders. And this is space-time. So we know that their parabolic host of measure of dimension with the one-dimensional host of parabolic measure will be 0 of their singular set. And currently, up to my knowledge, there is no better bound than this. And of course, not mentioning the fact that we don't know. So there are two things we don't know for Navier-Stokes equations. One of the things is uniqueness of these weak solutions in 3D. So on this, there has been some progress recently. Also using as a tool this epsilon-regularity results. So there's been progress by Jia and Sverak and numerical simulation by Guillaume and Sverak, proving that probably there is non-uniqueness of these L'Oreal solutions. And the second thing we don't know is whether there are singular points or blow-up points. So this gives an estimate about the size of the set of singular points, but up to my knowledge, we don't know better. So I will stop the lectures here. Thank you. Thank you very much for attending the whole lecture.
Thank you very much for your very interesting lecture.
Thank you.
Many are there any questions?
It's already late, so sorry that I took more time.
Okay, you consider Navier-Stokes.
Is it still a thing, or because I turned the mute on? But
Hi.
is it still is the question part of the video, or?
Please switch off.
No, I mean
it's okay.
as you like. Okay, so I can turn on if you like. Yeah.
Okay, so you can Navier-Stokes drift equation for. That is okay. That is because you need to estimate difference.
Yeah, yeah, because I have the estimate. I have the difference between between u theta k. So let's say a time variable is not here, minus the mean of theta k, and I have the nonlinear term, so u gradient u, and so yeah.
Okay, so you just replace. Okay, so mean value is constantly in space, so.
Yeah,
You just modify.
Yeah, this mean value is constant in space and time.
Oh, okay.
Yeah, not like the one of the pressure. Yeah. Yeah, so you. Yeah, when you write the argument, you have to be a little bit careful about this. Yeah. I mean, if there are other questions, I'm available to answer them, or if you don't want to ask them. And I'm staying for the week in Kyoto also, so if you want to discuss, you're welcome to.
Yeah. Okay, now let's thank the lecturer, Christophe, again. Yeah.